In this video, I'm going to walk through the steps for determining the Thevenin or Norton equivalent circuit for this example right here. This is an example from your Thevenin and Norton equivalent circuit worksheet packet. So as you've learned, in order to determine the equivalent circuit for some type of resistive circuit, what we need to do is we need to determine two parameters. We need to determine the open circuit voltage between the output terminals. And once we do that, we also need to establish the short circuit current, wherein we imagine connecting the two terminals together with a wire and determining how much current would pass through that wire with those terminals connected together. So there are a number of ways that we can do this. I'm going to suggest as a systematic way that I usually tackle these problems is to solve for the open circuit voltage using the node voltage method, and then solving for the short circuit current using the mesh current method. So let's begin tackling this. So as a review of the node voltage method, the first thing that we need to do is we need to determine the essential nodes of the circuit. I see that the essential nodes are the connection points between three or more elements, and those reside in this circuit right here. Alright, so I have four essential nodes. I'm going to designate one of my nodes as being my reference node, or my ground zero voltage reference point. So I'm going to select the low side of the power supply here as my zero voltage reference point, and that means I have three nodes that I need to contend with. Alright, since I have three essential nodes and then our fourth zero voltage reference node, I'm going to need three independent equations to begin with to determine what the voltage is at this terminal with respect to this terminal. Luckily, because of how the circuit is configured, I have a power supply or a voltage source that's directly connecting node A to my ground reference node. So I don't have to do any work for that node. I already know that the voltage at node A is equal to 72 volts. All right, now I need to do my current balance for node B to establish my one of the independent equations that I need to know. All right, so for node B, my equation is going to be the voltage at B minus the voltage at A, which is 72 volts. So VB minus 72 divided by 5 ohms. Remember, we're doing a current balance here, so voltage divided by resistance gives us current. That's through this path. I'm going to assume that B is always at a higher potential than all of the other nodes to which we're for which we're analyzing the current flow. So here we're going to go from node B, the voltage at node B, down to our reference node, which is 0 volts, divided by 20 ohms. And the third path that I have is from node B to node C, divided by the 8 ohms between the two of them. Kirchhoff's current law tells us that the current away from that node, all of those must sum to 0. Okay, so now I'm just going to do a little bit of algebra. I'm going to multiply by a common denominator here, and when I do that, I wind up with 8 VB minus 576 plus 2 VB plus 5 VB minus 5 VC is equal to 0. And collecting my terms, I wind up with 15 VB minus 5 VC. I'm going to move my constant term over to the other side of the equation, and I wind up with 576. All right, so that's one independent equation. I need a second independent equation now for node C. All right, node C is not necessarily an essential node. I only have two paths for current to flow out of node C, but I'm solving for that node because that's the voltage or the potential that I need to know with respect to my ground reference node. Alright, so again, the two paths, one will be from C to B, the other will be from C to A. I'm going to start off with C to B, so the voltage at node C minus the voltage at node B divided by 8 ohms is the current through that path. Again, I'm assuming that C is at a higher potential than B. Plus VC minus VA, which we've already determined to be 72 volts, is going to be divided by 12 ohms. All of that has to sum to 0. I'm going to multiply by a common denominator here, which is going to be 72. When I do that, I get 9VC minus 9VB plus 6VC minus 432 is equal to 0. Collecting like terms and moving my constant term to the other side of the equation gives me negative 9VB plus 15VC is equal to 432. So now I have two independent equations which I can solve simultaneously by any method I choose. I can either use substitution, or I can use my calculator to solve the equation simultaneously using linear algebra. And when I do that, my result is that the voltage at node B is equal to 60 volts, and the voltage at node C, which, since this is all with respect to our ground node, is also our open circuit voltage, and is also our Thevenin voltage, is equal to 64.8 volts. Okay. Alright, so I'm halfway through my solution now. I know that my open circuit or Thevenin voltage is going to be 64.8 volts. So if I'm to start my Thevenin equivalent circuit, my Thevenin equivalent circuit is going to be some resistance in series with a voltage supply that is 64.8 volts in magnitude. To determine this resistance, now what I need to do is I need to determine the short circuit current, as if I were to connect these two terminals together with a wire. So to do that, I'm going to redraw my circuit, and now I'm going to use the mesh current method to determine the current that would be delivered through this wire. Now remember that since we're connecting these two terminals for the short circuit current, our circuit has changed. So we cannot use any of the potentials or any of the currents that we derived in this first part of the solution. We have to solve again for the currents and the voltages, because this short circuit right here is going to change the amount of current delivered through the different resistive elements of the circuit. Okay, so as a review of mesh current, what we need to do is we need to determine, or we need to establish, some reference directions for our current flows. I have a mesh right here, a mesh up top, and a mesh that corresponds to this short circuit current that I want to know. I'm going to start with the current in the mesh that contains the power supply, and typically what we'd like to do is establish our reference direction for the current flow, which I'm going to call IA, so that it goes from the positive or the high side of the voltage supply to the low side of the voltage supply. So here we'll go clockwise. And the other meshes, it does not really matter which way we establish our direction. So I'm going to call the direction of current flow in mesh, in this mesh up here, I'm going to call this I sub C, and I'm going to assume it goes counterclockwise. And for the fun of it, I'm going to just arbitrarily assume that the current in this mesh, IB, is going to go clockwise. Okay. Now I need to write my voltage balance equations based off of Kirchhoff's voltage law for all three of the meshes. And this way I will come up with three independent equations that will allow me to solve for the magnitude of the current IA, IB, and IC. Right, so let's start off with mesh A. Right, the current, the voltage in mesh A is going to be 72 volts. That's gained here has to be dropped by the 5 ohm and the 20 ohm resistor here. All right, to write that, I'm going to assume that IA is our dominant current, so I'm going to make sure that I write that one first all of the time. I'm going to go IA, and I also know that through this 5 ohm resistor, I have IC current flowing as well. Both of those, at this point in the circuit, are flowing from left to right, so they're going to be additive. IA plus IC multiplied by the 5 ohms gives me the potential that's developed across that resistor. Here, across the 20 ohm resistor, I have IA current flowing, as well as IB. Now, in this case, IB is flowing opposite of the direction that IA is, so I'm going to subtract that from the total current. So the total current through the resistor is going to be IA minus IB, multiplied by the 20 ohms of resistance to give the potential that's developed across that resistor. And that both the potential developed across the 5 ohm resistor and the potential developed across the 20 ohm resistor, according to Kirchhoff's voltage law, has to be equal to the potential that's supplied to that mesh, which in this case is 72 volts. All right, just a little algebra here to regroup everything. When I multiply everything out, distribute my resistance values, I have 25 times the current IA minus 20 times the current IB plus 5 times the current IC is equal to 72. So that's one independent equation. I still need two more. For mesh IB, I'm going to repeat the same procedure, and I'm going to pretend that IB is the dominant current in this case. So I'm going to start off looking at this 8 ohm resistor right here. I have the IB current flowing through it, as well as the IC current. In this case, IC is going in the same direction as IB, so they're additive. Multiplying by the 8 ohms of resistance will give us the potential across that 8 ohm resistor. All right. That voltage, in addition to the potential that's developed across the 20 ohm resistor, here I'm going to assume that IB is dominant. IA is flowing in the opposite direction that I assumed for IB, so I'm going to subtract IA from IB to determine the total current through the 20 ohm resistor. Multiplied by 20 ohms gives us the potential, and since there's no voltage supply in this mesh, all of that has to sum to 0. All right, again, just multiplying my resistances, distributing them out, and collecting terms, I wind up with 20 IA plus 28 IB plus 8 IC has to be equal to 0. All right, for my third independent equation, I need to look at mesh IC. Again, mesh IC has no supply in it, so it's all of the potentials across the 5 ohm, the 8 ohm, and the 12 ohm resistor are going to have to sum to 0. And I'm going to start off with the 5 ohm resistor here and assume that IC is the dominant current. So IC, the other current that's flowing through the 5 ohm resistor is IA, and that's in the same assumed direction, so those are additive. IA plus IC gives the total current through the 5 ohm resistor multiplied by the 5 ohms gives us the potential that's developed across that resistor. All right, for the 8 ohm resistor, I have IC current flowing through that, as well as the IB current, which is assumed to be going in the same direction. So it's additive again, multiplied by our 8 ohms. And then the third resistor that I have to worry about in this mesh is our 12 ohm resistor. Our 12 ohm resistor has no other currents flowing through it, so the potential that's developed across that resistor is the IC mesh current multiplied by 12 ohms. Again, there's no external supply in this mesh, so the total, all of these potentials have to sum up to 0. And again, I'm going to multiply through and collect my like terms. I wind up with 5 IA plus 8 IB plus 25 IC must sum to 0. Now again, just to reiterate this, all of these equations were developed based upon my assumed directions for the current flow. It doesn't matter which directions you really assume. If you chose IC to go a different direction or IB to go a different direction, when we solve things out, all that will happen is that you'll get the correct magnitude and you'll get a negative sign on the result for those currents, indicating that you assumed the wrong direction for current flow. So when I take these three independent equations, I solve them simultaneously. I wind up with a solution that tells me that the current in mesh A is 12.72 amps. The current in mesh B is 10.8 amps. And the current in mesh C is negative 6 amps. Okay, so again, since I wound up with a negative sign for IC, that indicates that my assumed direction here was incorrect. I really should have assumed that this current was flowing clockwise, or in the real circuit the current will flow clockwise. But since we assumed that it was counterclockwise, we wound up with a negative value. The short circuit current that we're interested in corresponds to the mesh current IB. So this is the one that we're interested in. And that's our short circuit current, which is also the same thing as our Norton current. Now that we have come up with our mesh currents, our short circuit current, as well as our open circuit voltage, which we determined earlier to be 64.8 volts, I can use those results to calculate my Thevenin equivalent resistance. My Thevenin equivalent resistance for this circuit is given by the open circuit voltage, or the Thevenin voltage, divided by the short circuit current. Alright, so that was 64.8 volts. That's what we determined the open circuit voltage to be previously. We just determined that the short circuit current, or Norton current, is 10.8 amps. That gives us a 6 ohm equivalent resistance for our Thevenin circuit. So this circuit now, with respect to the two terminals that we use, these two output terminals, we can represent that in a simplified form as 64.8 volt voltage source in series with a 6 ohm resistive element. All right, and if we do any calculations on this, if we apply any different load resistance between these 2 points, it will behave as though it were this complicated circuit up here. We've reduced this complicated circuit now to a single power supply and a single resistive element. This is our Thevenin equivalent. We could also represent this circuit, if it's more convenient, as a current supply in parallel with a resistive element. The resistive element is still the Thevenin or Norton equivalent resistance that we excuse me, that we computed right here. So that is 6 ohms. And our current supply is going to take on the value of the short circuit current, or the Norton current, which was 10.8 amps. All right, so this circuit is equivalent to this one, is equivalent to the one that we solved originally.